Hello, everyone, and welcome to our first online lecture on minerals. If you saw the last one, you should know I'm much more comfortable now. I much prefer not being on the camera, despite the fact that in class y'all just sit there and stare at me, but for some reason it freaks me out being on camera. So, anyway, this is our first lecture on minerals, and I'm really going to gear it mostly toward helping you guys understand the exercise that I want you to do. But along the way, we're going to learn some stuff too. So let's take a look at the exercise real quick. Let me get out of PowerPoint and let's get into some Microsoft Word here, mineral exercise. So you can download this from my courses, and you need to do that. This isn't something you can do on my courses. And there's mineral identification, and here's some things that will review the things that we're about to talk about. And then ignore the points. This is kind of stolen from my online class where they have points. Ignore the points. Just do your best. It'll be fine. So then we have some pictures of minerals and then some information about them and that I would like you to identify. And so I tell you about them, and you're going to use that information to use this chart, also available online, to identify minerals. And so let's jump back to the PowerPoint and let's learn how we do that. Okay, so as I do this, I'm going to let y'all in on a little secret. I think you know this already, actually, that, when I'm lecturing in front of you, I know what slide is next. That lets me be a little more smooth in my delivery. Here, I think I know what slide is next, but I'm not sure. So if a slide seems to surprise me when it comes up, that's because it surprised me. I haven't figured out how to do that here yet. So anyway, so minerals. So this is a cool picture. This is a cave in Mexico. That has some of the largest minerals in the world. Those are crystals of the mineral gypsum. And gypsum, those crystals would normally be about the size of your finger. And yet there they are. And then, right in the middle, there's a person for scale. These things are huge, just huge. And actually, the location of this cave is actually a secret because they don't want people going in there and doing what people would do. And so, yeah. But minerals are very important. I mean, the wealth of a country is, to a large degree, really determined by its mineral resources. I mean, geologists have something we like to say, and it's absolutely true. If you look around you, everything you see was either grown or mined, and mining in this case would include pumping petroleum, right? And all of that is geology. I mean, things grow in soils. Soils is geology, but in particular, mineral resources. So all the metals you see around you, anything around you that isn't wood or plastic basically had to be dug out of the ground by somebody. And so, yeah, this can get geopolitically very complicated. Let me see, there we go. There's a picture of a Navy SEAL with all the gear that they would have, and then all of the chemicals that would make up that gear, and all of the places in the world it comes from. And so you can see that while the United States has a lot of mineral resources, we don't necessarily have everything. And so we have to buy, a lot of rare earth elements from places like China, South Africa, the Congo, places that are, politically unstable, maybe places that we don't really always get along that well with. And you can see how this would really complicate geopolitics, right? You're upset with the Chinese because, whatever, and suddenly they're like, okay, well, do you want those rare earth elements so you can keep making night vision goggles? Because you might not want to piss us off so much then, so you can see how this gets complicated. But it's not just, fancy military equipment, right? Your phone has all kinds of fancy little elements that have to be extracted from minerals from all over the world. And so, yeah, it's not, we are all dependent on each other as we are learning. So keep that in mind. When you think about the things that you want and need, it doesn't all come from here. It really doesn't. So, okay. So what is a mineral? Well, now that's kind of an interesting question. Um, to a large degree, it depends on who you ask, right? If I ask a nutritionist, what's a mineral, they're going to say something I don't even know what that has something to do with what you need for your body and this and that and on and whatever, right? But to a geologist, a mineral has a pretty specific five-part definition, right? First of all, it needs to be naturally occurring. So this leaves out any of the weird stuff that you see in, that people make in labs. Also plastics, things like that. Not a mineral. Okay. Now, we can make minerals in a lab. Diamonds, for example, is a mineral, pure carbon, that we make in a lab all the time. There's a lot of gemstones that we make in a lab, but you can also find them laying around on the ground if you go to the right place. And so, mineral. Generally inorganic. Now, organic, see my little air quotes around the word organic, okay, is a word that's been sorely abused. What a scientist means by organic is generally having to do with life or living systems in some way. Okay, so minerals are not alive. Okay, nor do they channel energy. I've spent my whole life around minerals, and my chakras are terribly unbalanced. I can tell you that. So yeah, none of that. But no, they're not alive. Now this brings us to an interesting place, though, because there are minerals in your body. For example, your teeth are the mineral apatite, which I just find funny. Teeth, apatite, haha, you get it. So anyway, mineral apatite. Your bone is made of the minerals calcite and aragonite. And as a paleontologist, this is really interesting to me because when you look at the fossil record, you find a lot of teeth, a lot of teeth. There are organisms that we just know from teeth, a lot of them. And so, and not nearly as much bone. Well, bone is chemically much more susceptible. And so if you have a skeleton just laying out, the first thing that's going to go away is the bone. And so it might only be the teeth that get preserved and incorporated into the fossil record. And so, by the way, if you want a big fancy word, the word for the disintegration of material in the process of fossilization is taphonomy, Taphonomy. So there's your big fancy word for the day. Minerals are solid, as opposed to liquid or gas. So that's pretty straightforward. But give me a second, and that's going to come back to bite us a little bit. Not bite us, but it's going to get interesting. Crystal structure. The minerals have a crystal structure. Now, what I mean by that, okay, is not that they're always great big honking pretty crystals like you see this fluorite crystal here. Okay, what I mean by that is internally, the atoms are stacked in a very specific and particular way. On the left there, you see kind of a molecular diagram of salt, which is the mineral halite, by the way. Speaking of the wealth of a society having to do with its mineral resources, salt was a very, very valuable mineral for a very long time, the mineral halite. But you can see how those sodium and chlorine atoms are stacked in a very regular kind of a way. The molecular diagram you see on the right is actually quartz, which is made up of something we'll learn is called a silicon-oxygen tetrahedron. Those are stacked, and those silicon and oxygen atoms are stacked in a very regular way. It doesn't mean that every time you see a mineral, it's going to be a nice, big, pretty crystal. It might just look like lump O mineral, okay? It might look like your fist, okay? It might look like nothing, right? Imagine me standing in front of the class right now, holding up a mineral that doesn't look like anything, okay? Even if it doesn't look like anything, internally, it's got that very regular stacking to it. And that's going to be important here in a few minutes. The last thing is minerals have a very definite chemical composition with some variation. So in other words, minerals have chemical formulas, right? Halite is NaCl. quartz is SiO2. Gypsum is CaSO4H2O, etc., etc. And so these minerals, they have chemical formulas. One time I shared a lab with a chemist. I was a teaching lab with a chemist, and I had all my minerals laying out, and the chemist walks in and says, "Oh, I see you have some silicon dioxide and some hydrated calcium sulfate and some blah 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 blah." They have different names for these things, but a chemist would look at a mineral and think of it as being a pure substance. So yeah, so this is a pretty good definition. It works well. If something meets all 5 of these criteria, it's a mineral. And so yeah, it does lead us in some interesting directions, though. I already talked about the generally inorganic, butt, bone, and teeth. But the solid thing kind of gets interesting. As simple as you would think that is, it's not. For example, what about water? Right? Water's not a mineral. It's a liquid, right? So, okay. What if I freeze it? Turn it into ice? Well, it's naturally occurring. It's inorganic. Now it's solid. It definitely has a crystal structure, right? I mean, snowflakes are an external expression of that internal crystal structure. And yeah, it has a chemical composition. You all know the formula for water. It's H2O. So yeah, ice is a mineral, oddly enough. The fact that it's liquid at room temperature doesn't really mean anything, right? Everything has a melting temperature. So, whatever. This seems silly and funny and, geologists, we go to parties, haha, there's a mineral floating in my gin and tonic or something like that. But I've shown you pictures of glaciers. That's ice. And suddenly there are geologists who are very interested in how that ice behaves under pressure and how it flows and how it moves and what it does and, the mineral properties, oddly enough, of ice. So yeah, so ice is a mineral. Water is not. Kind of fun, kind of weird, but there it is. So okay, so how do we identify these things, right? Okay, sorry. See, this is where the next slide surprised me. I was expecting something I didn't get. What's a rock, right? If that's a mineral, then what's a rock? Well, a rock is a combination of minerals. Now, when we look at this slide, we can see that the sentence is a little weird, a combination of one or more minerals. So I think we understand how we could have a combination of 2 or more minerals. This granite here, right? Granite is a rock. It's an igneous rock. We'll talk about this. We'll talk about granite in the next video. Granite's an igneous rock. And so it's a combination of minerals, right? It's got some quartz in it. It's got some hornblende in it. It's got some feldspar in it. Probably a couple different kinds of feldspar. And it's probably got some mica in it. And there's probably 10 or 15 rocks in that. You have 10 or 15 minerals in that granite. It is a combination of minerals. So when you look at granite, all those different colors you see, and maybe you have a granite countertop at home, go look at it. Pause the video, go look at it. I'll wait. Okay, now you're back. Cool. Okay, so all those little different specks of color that you saw in that granite countertop were different minerals. Okay, and as we'll learn when we talk about igneous rocks, I should probably put little air quotes around granite when I say countertop, because there's a lot of not granite countertops. Not a big deal, but there are. Now, so I think we understand a combination of 2 or more minerals. What the heck's a combination of 1? Well, we live in Florida. There's a piece of limestone. Okay. Now, limestone is an interesting rock. It actually does have a chemical formula, CaCO3, which when I changed my color scheme, I know that's a red-headed woodpecker. And you're like, why on earth is there a red-headed woodpecker in my PowerPoint? All will be made clear in just 1 second. I'm not going to try to move that because I'd have to get out of this presentation mode. Anyway, that's limestone. Limestone is a little bit unusual as a rock goes because it has a chemical formula, CaCO3. It's made out of calcium, carbon, and oxygen in that ratio. So why isn't it a mineral? It's naturally occurring, it's inorganic, it's solid, it has a definite chemical composition, but it doesn't have a crystal structure, right? Internally, that is mush. Oh, calcium carbonate. So it needs all 5, and it has 4 out of 5. So we kind of call that a combination of one mineral. I might more properly say a combination of 2 or more minerals, or something that has all the criteria for a mineral, but not a crystal structure. Meh, whatever. That's what I mean. Okay, so what the heck is up with the red-headed woodpecker? So here's the thing. We want to learn how to identify minerals, right? Identifying birds is pretty dang... Okay, so an ornithologist is going to beat me about the head and shoulders for saying this, but identifying birds is actually pretty dang easy. You have a bird book, and imagine me standing in front of the classroom now, holding up my bird book. It's got a bunch of pictures of birds in it. You see a bird, you want to know what it is. You look at the bird, you look at the picture, you match the picture to the bird, and that's what the bird is, right? Every red-headed woodpecker looks like this. Everything that looks like this is a red-headed woodpecker. It's that simple. It's not that simple, but it's that simple. Okay, so why can't we do that with minerals, right? Because we have mineral books. I have tons of mineral books. They all have pictures in them, pretty pictures. That's awesome. You don't identify them by the pictures. You just don't. They are not consistent enough, right? Look, there's 4 minerals. They all look more or less the same. They're all white to clear. They all kind of have flat sides. That is 4 different minerals. That is halite, calcite, dolomite, and gypsum. 4 different minerals, okay? And I could have easily put 6 or 7 more vaguely white, mushy minerals up there. I only had room for 4, okay? So how on earth do you tell these apart, right? You can't just look at a picture and look at the mineral. You just can't. And in a sense, they all look the same. But then in another sense, I could show you 7 or 8 pictures of quartz and they would all look different. So how do we do this? How do we identify minerals? Well, we do it according to certain properties. See, because minerals have a definite chemical composition, and because they have a crystal structure, there will be certain things that will be consistent, and we're going to use those things to identify the mineral. Okay, so what are these things? Well, color is not one of them. Okay, unless you have a great deal of experience, don't use color to identify minerals. There are some that are pretty consistent, most are not. You can see here on the left we have the mineral fluorite in 1, 2, 3, 4, 5 different colors. On the right we have the mineral quartz in 4 different colors. And so, if you learn that quartz is kind of white to clear, that's not going to work for you. You're going to come up against purpley quartz that we call amethyst, or that dark smoky quartz that's scarred by exposure to radiation. There's going to be all different kinds of colors of quartz. One time I was teaching minerals to a geology class, and we were learning to identify them in order to identify igneous rocks. And there's one mineral in particular, feldspar, that is pretty consistently pink. It is pretty dang consistently pink. And so I told them that. I said, guys, this is feldspar. It has this and that and that, and it's pretty consistently pink in color. That one's pretty safe. And then on the test, I accidentally gave them a piece of rose quartz, which is, as you may or may not know, kind of pink. Fully half the class looked at the pink mineral and called it feldspar, just because it was pink. We rely so much on our eyes, and most of us so much on color, that just overwhelms everything. So I need you, to learn to ignore, for now, the color of a mineral. Once you get a little more experience, you'll know what is and is not consistent, and it'll be okay. But for now, let's not worry about color. So if we can't worry about color, what do we worry about? Well, how about luster? Luster is the quality of the light reflected off of the mineral. There's 2 basic divisions, metallic and non-metallic. So metallic luster, the mineral looks like polished metal. The picture you have here is of galena. Galena is an ore of lead. It is valuable because you can extract lead from it. It is sold by the boxcar load. It is a valuable mineral. I mean, it's not valuable like if you find a piece you're going to be rich. Don't. It's not. I've got huge chunks of it. It's sold once again by the boxcar load. Okay, but it has metallic luster. When you pick it up and look at it, it looks like polished metal. You pick it up off of the ground, shake the dirt off of it, and it looks like polished metal. Okay, that is what we mean by metallic luster. The mineral pyrite also has metallic luster. Gold is a mineral, and it has metallic luster, right? Minerals with metallic luster tend to have metals in them, right? There are forms of the mineral hematite, which has iron in it, that have metallic luster. And so this is a good thing. You pick up a mineral, and if it has metallic luster and you recognize that, it narrows it down right away. Everything else is non-metallic. Now, in the real world, we would have several subcategories of non-metallic for oily, greasy, pearly, vitreous, adamantine, and all kinds of different things. We're not going to worry about that. We're just going to divide them into metallic and non-metallic. Here's what I want you to keep in mind, though. Metallic is not sparkly. Okay. In other words, if you have a diamond, look down on it right now. If you don't, just think about one. That's very sparkly, and that particular luster is called adamantine luster because the refractive index of the diamond is actually high enough that the light is bouncing around inside of it, and it literally can't get out. That's why diamonds have that sparkly bit. But that's not metallic, right? That's not metallic. It doesn't look like metal. Okay, so keep that in mind. So if it looks like polished metal, it's metallic. If it doesn't, it's non-metallic. The overwhelming majority of minerals that you encounter will be non-metallic. So when you pick up a mineral, unfortunately, you all will not be able to. But going forward in your life, if you need to identify a mineral, you pick up a mineral and assume it's non-metallic until you can show otherwise, right? So yeah, now in the exercise you're going to do, I'm going to tell you whether or not it's metallic or non-metallic. So yeah, okay, so luster, metallic, non-metallic. Another property that's very useful is hardness. Now hardness is a very misunderstood property, and excuse me while I take a sip of coffee. Oh good, okay, so hardness is a very misunderstood property. It is the resistance of a mineral to scratching. That is I said it like that because that is a very specific thing. Scratching, not breaking, not crushing, but scratching. Okay, and so you see these TV shows where diamond is the hardest mineral. It's a 10 out of 10. On what we call the Mohs hardness scale. What that means is that diamond will not scratch. Diamonds will absolutely break. They will absolutely chip. And so, yeah, so you'll see a TV show. I saw this once on one of those CSI shows where they had this big thing and they're like, well, let's test and see if it's a diamond, right? And they put it between these two jaws and they crushed it. And so they used some fancy words and they said, that's not a diamond. It broke at Mohs 6. And I'm like, okay. That's not even what Mohs is, and y'all just crushed a diamond. So, or may have. So anyway, scratching, not breaking, not chipping, but scratching. And so we have a scale that runs from 1 to 10. And you can see it there. So there are certain minerals that, we know have this particular hardness. So talc is a 1. Talc is the mineral that you would grind up to make talcum powder, right? No one wants to be putting ground up topaz on their baby's butt, right? Talc, okay? Gypsum's a little harder, calcite's a little harder, fluorite, apatite, orthoclase, feldspar, quartz, topaz, corundum, and then finally diamond. Now, this is not a linear scale. In other words, diamond is way, way, way harder than corundum. And corundum is actually way harder than topaz. So it's not like, the 4 is twice as hard as the 2 and the 8 is twice as hard as the 4. It doesn't really work that way. So And so if you want to determine hardness in the field, you can order a box, or just, go into your, mineral collection and assemble, a piece of each of those minerals. None of us have diamond because, we're geologists, we're not rich. So, but, 1 through 9 is good. And then, you could take that into the field and you can just kind of plop down in front of a mineral you're not sure about and start scratching it, right? And you say, well, um, okay, so the apatite scratched it, so it has to be softer than a 5, but the calcite, didn't scratch it, so it has to be harder than a 3, so it's somewhere between a 5 and a 3, so maybe it's a 4. What minerals, have a hardness of 4? It's not just fluorite, there's, hundreds of them, and you start to narrow it down. And you could do that, but we're going to laugh at you because we don't actually do it that way. See that knife over there? We carry a knife, okay? And what you do is you pull out your knife. Not a good knife because you're going to be scratching minerals with it. But a knife has a hardness of about 5.5. Scratch the mineral. If the knife scratches the mineral, it's softer than 5.5. If it doesn't scratch the mineral, it's harder than 5.5. And a lot of times that will get you where you need to be. There's a lot of minerals that look very similar to each other that are on either side of that 5.5. For example, calcite and quartz. You can see on here, calcite has a hardness of 3. Quartz has a hardness of 7, but they can look very similar. And they're also both very common. So if you have something that looks kind of white and milky, odds are it's either quartz or calcite. Pull out your knife. Your knife will scratch the heck out of the calcite and won't even touch the quartz. And so we do that a lot. And if you do it enough, you can kind of learn by feel and narrow it down even more than that. So hardness. Very useful property. Resistance to scratching. Very specific thing. Not breaking. That's tensile strength. That's a whole other property that we're not even going to talk about. Okay, so another handy property is cleavage. Which is the tendency for the mineral to break along very flat surfaces that are planes of atomic weakness. So in other words, remember I talked about that mineral matrix, or that chemical matrix that mineral has, that internal crystal structure. There's going to be weak bonds in that crystal structure. There are several different kinds of atomic bonding. Some are stronger than others. Covalent bonds are stronger than ionic bonds. So here we have a mineral, and it might be covalently bonded in this direction, and I'm pointing in the upper left-hand part of the picture in case you can't see it. It might be covalently bonded in this direction, which would be a very strong bond, but ionically bonded in this direction, which would be a very weak bond. So I could take something and wedge it in there and get that mineral to break very, very flat, or seriously, I could throw it on the ground and it would break. And it would tend to break. It's not that it won't break this way up and down, but it will prefer to break back and forth from the point of view of this picture. And it'll break very flat. Now, a couple things. Don't confuse cleavage with the crystal, right? Because a lot of times you'll pick up a mineral and it'll have, really pretty crystal. That's how the mineral grew. It may or may not be how it broke. Quartz, for example, and I know I have a slide on this, so give me 1 second here to find. Yeah, it's past all of these. I'll show you these here in a minute. There we go. So quartz, for example, makes these really pretty crystals that you can see in the upper left here, right? But if you break it, it just shatters. It just breaks. It does not have cleavage, okay? And even minerals that do have cleavage will usually, but not always, break along those crystal faces, right? And so I actually have a video by a geologist on cleavage that I want to show you guys, and this is going to be new, so let's try it and see how it works. And I need my browser here, and I need this, and I need this, And I'm going to unplug my microphone and I'm going to hit play so that you can hear this guy. Alrighty, let's give this a try, guys. Hi, we're taking a look at cleavage in minerals here, and this is a piece of gypsum. And I'll be demonstrating how it cleaves and the three different directions in which it cleaves. Here's a closer look at that piece of gypsum, and it has nice, flat, smooth surfaces, as you can see. And what I'm going to do is see if I can't split along that particular surface. And I'm not going to use a hammer. I think I could probably do this just with my fingers. All right, there, cleaved. That's a perfect cleavage, producing nice, flat surfaces guided by the atomic structure. All right, let's take a look at the thinner piece here. See if I can't cleave that one again. It's cleaving coming off in a bunch of little pieces here. There's a small piece right here. So you can see it does break again and again. I do have a knife here. I'll slide this along cleavage direction. Produces a little better one. Right? And if I had more patience, I could probably split that again and again and again, so that you can see that gypsum has cleavage guided by the atomic structure. But looking at this piece right here, I noticed that there's a little line right across there. That's an incipient cleavage plane. I'm going to break it along that line. However, I also want to show you another physical property of gypsum, and that is that it has flexible sheets. So I can take this one right here and apply some pressure to it, and you can see that broke along that incipient cleavage plane there. But this piece right here, you can see how it's bent. Right? So that bend it a little more. Gypsum is flexible. Right? Continue to break it here. There's that broken chunk here again. So the cleavage directions that are produced so far are top and bottom, this side, and the side my thumb is on, and again over at these two sides. So that's one direction, two directions, three directions of cleavage, and they'll repeat themselves. Now I already repeated it along the flat direction there that produced the thin sheets, but I can reproduce it in that direction parallel to that side. So I'll take it. It bends a little bit. Alright. So that's the cleavage in that direction. And along this direction here, parallel to where my fingers are right now, there's one. Another one. Maybe one more. Yeah. Alright. So you can see these are all cleavage fragments here. Gypsum has perfect cleavage in one direction, producing these thin, flexible sheets, and two good directions of cleavage otherwise. Right? So that's gypsum. This is a closer view of all the little fragments that were produced by that process. Right, this is all the gypsum fragments. Look at those out of the way. Bring in this one piece right here. What I want to show you here is the difference between the cleavage in gypsum compared to the cleavage in muscovite mica. So let me cleave this one here again, get a nice thin sheet. Okay, that broke. Nice. And I do happen to have a piece of gypsum or muscovite mica over here. And you can see there is some similarity. There is a big difference. Gypsum has cleavage in three directions and mica has cleavage in one direction. But the other thing I wanted to show you was that gypsum has flexible sheets. So you can take it and you can bend it, and if I bend it too fast it'll break, but it does bend and it stays bent. Whereas a sheet of muscovite mica, you can bend it, but it'll snap back. Muscovite mica is elastic. It bends, but then it snaps back. Now this is a pretty thin sheet of mica here, and it would be difficult to cleave
This is a nice flat surface produced by cleavage, as is the opposite side. And along the edges here, instead of producing straight surfaces, it breaks with an irregular fracture, unlike the gypsum, which has more cleavage directions.
Okay, I'm back, and we don't need that anymore. So let me stop. There we go. Calcite. Ooh, what fun. Okay, let's not do that though. Okay, so all right, let's go back to the PowerPoint, and I'll just come down here and PowerPoint. There we go. Okay, and so yeah, so let me show you some different pictures of some cleavage. So when we think about cleavage, we think about a couple different things. We think about how good it is, and that's what he was meaning by perfect or good or okay or bad or whatever. Perfect cleavage will make a very, very flat surface. This is mica, the mineral that you see here. That is like the mineral that that he was showing you. That great big flat sheet at the end was a beautiful piece of mica. I'm very jealous of whoever that geologist is, by the way, because I'm stuck up here without any of my rocks or minerals, and I miss them. Anyway, one perfect plane of cleavage. This is the mineral feldspar. This is kind of what two cleavage planes look like. Notice that that you got a nice flat surface here, and you got a nice flat surface there. But look there, see how it's irregular, kind of chunky? That's not cleavage, that's fracture. Okay, so now we have two directions of cleavage, one going this way through the crystal and one going that way through the crystal. Here we have two cleavage planes, but not at 90 degrees. Notice here, these two cleavage planes are sitting at this angle right here is 90 degrees. Oh, I can change my pointer. I'll bet I can. Oh, let's try something fancy. Laser point. There we go. Yeah, better. So sorry guys, I am so learning this as I go. Anyway, cleavage plane here, 90 degrees in between, right? And so yeah, here, cleavage plane here, not 90 degrees in between them. In fact, that's 120 degrees. And so, we worry about cleavage direction, how many it has. We worry about how good it is. We worry about the angle in between the planes if there's more than one plane. This is the mineral halite. This is salt, and it has 3 cleavage planes, 6 sides, but sides that are parallel to each other are one direction through the crystal. And so you can see, a flat surface here with a matching flat surface here that you can't see. Flat surface here with a matching flat surface over there, a flat surface here, and a flat surface there. So 3 cleavage planes gives us a cube, and there are calcite pieces of calcite that really are just perfect cubes. If you were to lick that mineral, it would taste like salt. It is salt. Here's a mineral. Here's mineral calcite. Also 3 cleavage directions, but notice now they're not sitting at 90 degrees. The smaller angle here is about 75 degrees, and so calcite and halite are very common minerals, and that's how you tell them apart. Otherwise, they're both going to be more or less the same color. They're both going to have the same hardness. They look very similar. How you tell them apart is the angle between the cleavage planes. That's assuming you don't want to lick it. That tastes salty. That does not. Don't go around licking minerals. Right? If you're not going to taste your face, you're certainly not going to go around licking minerals. Okay, no touchy. Okay, so, but the angle of the cleavage planes is really, really the thing here. And so this is kind of fun. This is the mineral fluorite. You've seen pictures of this before. Fluorite makes crystals that are cubes. Hold on one second. I'm going to get out of this view. I'm going to run up here because I put a picture of fluorite right here. This is fluorite. It makes crystals that are these cubes. Let me get my laser pointer back. I like my laser pointer. It makes crystals that are cubes, but when it breaks the corner off of those cubes. The cleavage and the crystal are not related. I mentioned that to you before. And so if I take that purpley cube and I break it along all 4 cleavage planes, in the end, what I get is that. This little diamond-shaped, what we would call a rhomb. The interesting thing is the reason that is called a diamond shape is because the mineral diamond also has 4 planes of cleavage. If you just cut a diamond where it naturally wants to break, that's what you're going to get. All those different facets in that diamond have been put there by people and stuff. But naturally, that's what a diamond would look like. So, and in terms of shape anyway. So yeah, so that's what we worry about. Now, the good news is, I'm not going to make you all identify cleavage planes because you don't have minerals at home. And so in the exercise, I'm going to describe the mineral's cleavage to you, and then you'll use that to identify. And as I mentioned earlier, not every mineral has cleavage, right? This is the mineral quartz. It makes these nice, pretty, toothy looking crystals, but if you break those crystals, they just shatter into something that is called conchoidal fracture. You can see that, when it breaks, and I'm going to get my laser pointer back now that I know how to do that. You can see when it breaks in these kind of hollowed out areas. And if those meet, you can make something that is pretty dang sharp. This property of conchoidal fracture is what people look for when they're going to make arrowheads and stuff like that. Quartz is not the only thing that does it. Obsidian, volcanic glass breaks like this too. And there's some other things that break like this. And there's a site not too far from here that I'm going to do a field trip to and record for you guys that also where also conchoidal fracture will come into play. So we'll have a look at that in a few days. So another property that's useful is streak. So there's a piece of pyrite there. That's not the best piece of pyrite in the world, but that's okay. It has metallic luster. And like I said, that's not the best piece of pyrite in the world, but it has metallic luster. The other fun thing about pyrite, though, is that it has a streak. Now, what is streak? Streak is the color of the mineral when it's been powdered. And so now you're all like, I got to powder a mineral. How am I going to powder? Yeah, it's not hard. You have a little piece of unglazed porcelain, about 1 inch by 1 inch. And then you take the mineral and you rub it on the porcelain, and it rubs off. That color is consistent, where the color of the mineral varies from one, sample to another. They will always have the same streak. Minor amounts of impurity that can radically alter the color of a mineral will not alter the streak. Pyrite is a mineral that has something called incongruent streak, where the mineral is one color and the streak is another. You can see there that you got a yellowy metallic mineral that has a dark gray streak, right? This is one of about 20 ways to tell pyrite, which is sometimes called, as you know, fool's gold, from real gold. It really does take an idiot to confuse the two, by the way. And actually, people around here are paying for gold. I might buy a gold panning kit and go out and see what I can find and show you guys. So anyway, so incongruent streak. Not every mineral has incongruent streak, but when they do, it really jumps out at you. This pyrite, you have a yellow mineral and suddenly it streaks dark gray. Hematite is a kind of a grayish mineral that streaks red, and so it's a very, very useful property, and it's really easy to carry around one of these little porcelain plates, and just, if you're not sure in the field, just pull out your porcelain plate, pull out your mineral, and rub it. It's dead easy, and you won't be thought a fool for bringing a piece of pyrite into an assayer's office to think it's gold. Yeah. So, okay. Crystal shape. Now there is some pretty pyrite. Both of those pictures are pyrite, and it has a couple of different ways the crystals can look. Usually, it's those cubes that you see on the right, but you can see very distinctive crystals. Also, you can see how pyrite makes those nice cubes and also nice metallic luster. Now crystal shape is different from crystal structure, right? Crystal structure is internal. It's how those atoms are stacked internally. Crystal shape, on the other hand, is what does the crystal look like? Now, you might not always have a crystal, right? Having a crystal requires ideal growth conditions for a long time, and you might not have that, okay? But if you do, you're going to get a very distinctive shape. Most minerals will have maybe one, maybe two common shapes. But yeah, I mean, one or two, not a whole bunch. Those atoms, there's only a few ways they're going to stack. Now there are a lot of different crystal shapes. They can be fibrous or bladed or banded or cubic or any number of different things. We do have a way to describe crystals called Miller indices or Miller index, but that's way deep into crystallography weeds, and we don't really want to go there. So, for our purposes, we just describe what the crystal looks like, and that's fine. So, yeah, by the way, that fibrous mineral in the upper left is asbestos. Stay away. No touchy. Okay, so density is good too, right? Density is really handy. We usually call it specific gravity when we talk about mineral density because it's technically a little different, but really practically not. We've been in and out of density, for a while now, and some minerals are kind of heavy. I mean, if I passed around a piece of that galena, it's got lead in it. It's heavy, right? On the other hand, most minerals have about the same density as rock, around a 3. And of course, you can see my piece of pumice floating there. Pumice is not a mineral; it's a rock, but it's a really cool picture. So there you go. Sorry guys, but there is a way to. I'm sure I could edit that out. I have no idea how to do that. Density is handy. You can actually measure it, or you can just kind of hold it in your hand and get an idea about it. But it's a very handy thing because a lot of minerals do have very heavy elements like lead or even uranium, things like that. And so they're going to be heavier than you just kind of intuitively expect them to be. And then there's a few other, okay guys, there's about 20 more mineral properties. We're not going to talk about them. I mean, there's a bunch of them. There are a few others that bear mentioning though, just on one PowerPoint slide. Magnetism. There's a mineral called magnetite that has enough iron in it and enough alignment of that iron that magnets will actually stick to it. Double refraction is kind of fun. Look in the upper right. That's a piece of calcite. And do you see how when you look through it, you see two versions of the word double refraction? As the light passes through the mineral, it gets broken into two beams. And so as long as you're not looking down the optic axis, which is way deeper in the optical mineralogy weeds than you guys ever want to go, as long as you're not looking down what's called the optical axis, you will see two of what you're looking at. It requires a very clear mineral, but two. And then reaction to HCl, which is hydrochloric acid, some minerals and rocks will dissolve in hydrochloric acid. This is very important to us here in Florida, actually, and I should probably have a picture of this, and I might do a little thing about this and put it up as a supplement. But this is what makes sinkholes, y'all. Right? Not so much in Pinellas County, but if you go over toward the center of the state, you will see sinkholes. In fact, I cannot help myself. Give me 1 second here. And because I'm going to pull up Google Earth. I don't even know. That's the exercise. Yeah. I'm going to pull up Google Earth and I'm going to show you guys. So give me 1 second here and we will get this going. So here we go. And you're going to load all my stuff. So how you guys doing? Staying in? Getting stir crazy? I know I am. So if you want a list of places to go out and walk in Pinellas County, let me know, because I know a bunch of them. And most of them are still open. Okay, so here's Google Earth, and all of my personal Google Earth bookmarks. But if we look in Florida, and so let me get north up, and we look, there we are, of course, over here in Pinellas County. But if we come over here, look at this, look at this, right? And let me get rid of borders and labels real quick here, so we don't need those. Look at all these. These are lakes and these are sinkholes, right? And what's happened here. Remember, I showed you that picture of limestone? And I said it has everything it needs to be a mineral except for that crystal structure. Well, it chemically will dissolve in very weak acid. And so, you get rain, it filters down through those pine needles, and it gets a little bit acidic with an acid called tannic acid. Next thing you know, it's running through our bedrock, which is limestone, and it's dissolving it. And so if you have an area like the center of the state, where the bedrock is pretty exposed, there's not a whole lot of sand over the bedrock, you will get sinkholes, because as it dissolves that bedrock, it collapses down. And so, and so that proclivity of some minerals to dissolve in hydrochloric acid affects us directly in the form of limestone dissolving as groundwater runs through it. I'll give you another fancy word for this. The word that we use for this is karst, with a K, K-A-R-S-T, topography. And if you Google that, you'll see a lot about that. Conductivity, both of electricity and heat and whatnot, are important properties. And also, by the way, a lack of conductivity, right? Some minerals will conduct electricity really well. Copper is a mineral. It's also just a metal, but it's also a mineral. But then remember that big sheet of mica that guy showed you in the video? That does not conduct electricity. And so if you're building a circuit board and you want an insulator, if you don't want electrons moving from one place to another, stick a piece of mica in there. It will not let them go. It will not. And so that's a pretty handy property, actually. Piezoelectricity is just one of my favorites. Maybe you have a watch that says quartz movement on it. That doesn't mean that there's a bunch of little quartz crystals in there shaped like gears. What that means is that there is literally a piece of quartz inside of that watch. And when you run electricity through that piece of quartz, it vibrates. And it vibrates at a known constant rate that you can use to tell time, to keep track of the passage of time. I don't know what the rate is. I keep meaning to find out. I never do, but it's a rate. And so that's how quartz watches keep track of time. That property of vibrating when you pass electricity through it is what piezoelectricity is. The other fun thing about quartz is, by the way, if you bend it, it makes electricity. So it's kind of a weird little mineral. A lot of fun. So anyway, so we use these properties to identify minerals, and I'm going to show you how here in just a minute. We do have different mineral groups, and I am not going to go on too much about this because this gets a little bit deep in the weeds. But the main mineral group that we're going to worry about really are the silicate minerals. The two most common elements in the Earth's crust are silicon and oxygen. That is not oxygen you can breathe. That's oxygen tied up chemically in solid materials. And if I take silicon and oxygen and put them together, they make something called a silicon-oxygen tetrahedron. And the silicate minerals are combinations of these tetrahedra with different chemical elements stuck in between them and stuff like that. These are the minerals that make most rocks. Most rocks are made from silicate minerals, and I think, yay, that's what's coming. Okay, so the silicon oxygen tetrahedra that you see here can link with each other. And now this is going to be important later on. This linkage where you have either individual silica oxygen tetrahedra or single chains or double chains or sheets or three-dimensional networks. Geologists have this stuff tattooed on our eyelids because this controls all kinds of things. This controls how explosive your volcano is going to be. If your volcano has a lot of these structures, it's going to explode. If your volcano has a lot of these structures, it's going to ooze, like, say, Hawaii, right? If your rock is made out of a lot of these structures or these minerals, it's going to chemically break down very quickly. If your rock is made out of these structures, it's not going to chemically break down very quickly. When you go to the beach, don't go to the beach. Beaches are closed. Don't go to the beach. But when you do go back to the beach, most of that sand that you see on the beach is quartz sand. Because by the time it's flowed from wherever it's flowed from, that's all that's left. All this stuff is gone. Now, we can go to a black sand beach in Hawaii and see some of this stuff, and maybe I'll show you some pictures of that. But, yeah, no. So the silicon oxygen tetrahedra and the combinations of them are very, very important to geologists. They will be less important to us because we're not going to go deep in the weeds with Bowen's reaction series or melting and this and that minerals. But they are, if you go on in geology, you will be very, very familiar with these different silicate structures because they really are very important. Now, interestingly though, there are other mineral groups, non-silicate minerals. There's carbonates, there's halides, there's sulfides, there's all kinds of things, including, by the way, native elements, right? There are some things that are single elements that you really do just find laying around on the ground, right? Gold, copper, diamonds, sulfur, graphite, silver. These are all minerals, right? Because remember, they meet the 5 criteria, right? So these are all minerals. Look over here. Here's what we use them for, right? Their economic use. And this is the thing. These are less common, but they're more valuable. Look, silicon and oxygen, meh. We don't need that stuff, right? We need some, we might need some of it to make computer chips and stuff like that, but not so much. This stuff, oh, we need that stuff, right? Those are the minerals that have all those little tricky little rare elements in them and things like that we need to make our iPhones and stuff like that. So the overwhelming majority of stuff that you see is this, although not you guys, because you're in Florida. And it's all limestone. Okay, but go anywhere else. The majority of stuff that you see is this. This is the stuff that we really need. And so, there's a whole field called economic geology that is seeking to find that stuff. And I believe that's the end of my PowerPoint. Okay, so excellent. Let me show you the exercise. So there's our sinkholes. Okay, so the exercise itself looks like this, right? You want to download it from my courses. And so the exercise itself looks like this. So you got pictures of minerals. Look, guys, I just put pictures in there to make them look pretty, right? We're not going to use the pictures to identify them, right? We're going to use this stuff, right? We're going to use these descriptions. Okay, so the other thing that you need is this mineral identification grid. Now, this is on my courses, but you need to download it, okay? You need to download it because the formatting on my courses is weird, okay? So don't try to use this on my courses. Go ahead and download it, okay? So we've got tabs. Look down here at the bottom, right? Metallic, and then dark colored non-metallic, light colored non-metallic, okay? So what you want to do is look at the description and use this grid. I went too far. This grid to key it out. Okay, and now I am aware that this is probably the first time in your lives you've ever had to identify anything, probably much less with a key. Okay, but have a go at it. It's not so bad. Okay, so and so let's do the first one together. And I just realized I can do this. I'm gonna pull this up and I'm gonna make it smaller and I'm gonna put it over here. So let's look at the first one. So first of all, unless I tell you it is metallic, assume it is non-metallic. Okay, so I tell you the mineral is light in color. Okay, great. So we want to be we want to be on the light colored non-metallic mineral tab, not the dark colored one, not the metallic one, the light colored one. Let me get the thing back up. So what do I tell you? Clear to white, very soft. And so that's going to be a hardness of less than 5, right? You can see the first column of our key is hardness, right? I tell you it's very soft. That's going to put it down in here somewhere. Okay. So the next question is, what about its cleavage? What kind of cleavage does it have? Well, I say, look, it has 3 good planes of cleavage that meet at 60 and 100 degrees. Okay. So cleavage, excellent to good. So now absent. See, we have a choice here, right? Sorry, guys. We have a choice here. I've had too much coffee, I think. We have a choice here between cleavage being excellent or good or absent. Well, I tell you that, it's good. So that puts it up in here. So now we're narrowed down to here. One of these. It's a calcite, halite, gypsum, or muscovite. Okay, so meets at 60 and 120 degrees and will react to hydrochloric acid. Ooh, that's a good thing to know, right? So I look here, white, look, this one is colorless to light, cleaves into thin sheets. That's not it. Very soft, flat-bladed crystals. That's not a flat-bladed crystal, and it's not that soft. Here we have something, 3 cleavage planes were close, but they meet at 90 degrees. These don't meet at 90 degrees. These meet at 60 and 120, which leaves us with, sure enough, let me get my picture back. Sorry, guys. There we go. Sure enough, calcite. So, type calcite right in there and move on to the next one, right? So dark in color, soft with excellent cleavage along one plane, breaks into thin sheets. This would be one that's pretty familiar to us. So you want to be on the dark colored non-metallic tab, etc. Let's do a metallic one. So down. Here we go. Right, this one's familiar to us, right? So metallic luster. Okay, so we want to be on the metallic page, on metallic tab rather. So there's the metallic tab. There aren't that many metallic minerals to worry about because there aren't that many metallic minerals. But anyway, let me shrink this a little bit so we can see. Okay, so metallic luster, we're on the right tab. Hardness greater than 5. Okay, we're up in here, right? We're up in here, hardness greater than 5. That's narrowed us down to pyrite, magnetite, and hematite. No cleavage. Okay, all the ones up here are no cleavage, so that's fine. That doesn't help us, but that's fine. A dark gray streak despite having bright yellow crystals. Well, look, we look here, silvery gold, cubic crystals, right? This is the one, right? It's not dark gray to black or strongly attracted to magnets. It's not steel gray to reddish brown. Doesn't show any signs of rust. So there we are, pyrite. That might not have been the best description in the world, but it got you there. So pyrite. I should probably add something about the streak. So anyway, okay. So look, I mean, like I said, I know this is the first time you'll have ever done anything like this. So just take a breath and work through it. Okay, don't stress out on me about, oh my gosh, am I going to get this right or not? Just work through it. It's fine. Okay. Here's a review of what you need to do. Once again, ignore the point. Just do your best and it'll be fine. Okay. Alrighty, I think that's everything. I really hope this recording worked because I do not want to have to go back and do that all again. Oh, look, I think it did. Okay. That's it, guys. Thank you very much. And look for a lecture on igneous rocks coming up within the next day or two. All right. It's the weekend. Have a good weekend. And I'll talk with you guys later. Get in touch with me. Email is still fine if there's anything I can do. All right. Take care, guys. Bye-bye. Don't touch your face. Bye.